Okay, we're going to start in section 4.4. But this is generally just applications of logarithms, so we could call this logarithms continued. So if we go through these problems here in a little bit and you're confused, right now is really when I want to clarify any of the confusion about logarithms. Remember that logarithms are a function that spit out an output. So what I mean by that is that this is essentially like saying the function of some, let's say, x value. And then it spits out your output, which is your y value. So that's how you really need to think about logarithms, because otherwise it doesn't really make a whole lot of sense when we throw them stuff into the calculator. For instance, if I said evaluate or simplify the expression log of 35, right? The question might say evaluate log 35. There's a lot of stuff that goes unsaid here. And one thing is that, log where you don't have a base is called the common log. And the common log has a base 10, which is supposed to be understood, but never gets explicitly stated. So you might ask yourself, well, how do I go about solving a problem like this? And you don't have to think too deeply about it. All we need to do is throw this into the calculator. The calculator is going to perform the function of taking this log and then evaluating whatever the log is, log base 10 at 35. So practically, that's how we treat logs, and that's how you'll get through this section a lot of the time. So let's throw log 35 into the calculator. If I did that, there's a button here that says log. And if I throw 35 as my argument into the log, the calculator will simply spit out a number. So somehow log of 35, or log base 10 of 35, is 1.5440680. Again, lots of decimals there. So we could say log, if you wanted to, base 10 of 35 is equal to 1.544068044. And technically this number continues. Again, the calculator has a finite memory, so it just can't simply spit out an infinite number of decimal values. So it stops here at about like 8 decimal places. But in any case, this is close enough for government work. Whenever we're working with logs or exponentials, if the instructions for the question say evaluate this expression, then you're simply going to throw it into the calculator. It's going to spit out an irrational number with a bunch of decimals. And usually the question will say round to 4 decimal places. It'll tell you how many decimal places to round to. So in that case, we would go out to the 4th decimal place, which is the 0. And we're going to check to see if the neighbor is large enough to round this up. And sure enough, 6 is big enough to round that up to a 1. So what we can say is that log base 10, or just log of 35, is equal approximately. And so I put a little squiggle above the equal sign because the little squiggle indicates approximate. Sometimes you see just a squiggly equal sign. Again, that just means approximately. It's approximately equal to 1.5441. Okay. Does anybody have any questions about that? Any questions at all? Okay. It seems a little bit strange, again, because what this expression is really telling us, if we say, okay, log of 35 is approximately equal to 1.5441, we could convert this into exponential form if we wanted to. We could say that the base of 10 raised to this exponent, 1.5441, should get us pretty close to 35. Again, this is logarithmic form. And if we wanted to understand it a little bit better, we could switch into exponential form, which I think has a more intuitive understanding. 10 raised to this number should get us pretty close to 35. And let's see if the calculator can get it pretty close. So 10 raised to the 1.5441, pretty close to 35. Right? So whenever you see a logarithm with a number in there, that is just its own number. It's weird to have that in an equation, but because it's a number, you can manipulate it in an equation the way you would manipulate any other numbers. You can add, subtract, multiply, and divide a logarithm with an input to both sides of the equation, using all the principles of solving equations that we've seen up to this point. So what we need to do is look at a couple of problems that just say simply find the value, which is another way of saying evaluate. Give an approximation to 4 decimal places. So log 2.58. Then we'll want log of 4.43 times 10 to the second power. Okay, so how would you go about solving these? Since they're just giving you a log and some input, you're literally just going to put this function into the calculator. It's going to spit out some decimal number, and that's your value. Once we get the weird decimal number, we'll just round it off so that we only have 4 decimal places. So again, log, this time we're looking at 2.58. And we get 0.411619706. Okay, so if you wanted to, you don't have to show me that you rounded. It's approximately equal to 0.411619706. And then if you want to show me that you rounded to 4 decimal places, I always underline the 4th decimal place, circle the 5th decimal place, and if the 5th decimal place is large enough to round this number up, then we do so. But if not, we just leave it alone and we just cut off the rest of the values. So this will be the answer for this particular problem. Does anybody have any questions? Okay. Has anybody gone ahead and evaluated the second part or the second problem?
Yes.
What did you get?
2.6464.
Let's see. Okay, so I'm just throwing it into the calculator exactly the way it was written down. And there we go. So we get approximately, and if you wanted to round this off immediately, you could, 2.6464, and then the last decimal place is a 0, or the 5th decimal place is a 0, the last one that we're concerned about. So it just, we'll leave it alone, 6464. Any question about those? Seems pretty straightforward. Plug and chug, right? Plug and chug. But we might have some that are like this. Log 307 plus log 15. So how do you think we go about evaluating or finding the value for this problem?
Figure out each one individually and then add them?
Yeah, absolutely. Or you could throw this directly into the calculator as an expression where you're just adding log 307 plus log 15. So if we did that, and just throw it in the calculator, log 307, close the parentheses. So you want to be very careful to close the parentheses there before you add log of 15, because we should be getting 3.663. I guess we can add that the fourth decimal place there. And that should be our answer. But if you make the mistake of not closing the parentheses, so let's say that you put log 307, and then you didn't close the parentheses and you put plus log of 15, and then you close one set of parentheses, then this is almost as though you plugged in this other log inside the argument of the first log. So you would get some different value. Okay. So with these kinds of problems, because we're throwing them in the calculator willy-nilly, just sort of mindlessly doing that, you need to be sure of what you're typing into the calculator and that you don't accidentally type the wrong thing, because user error here is really going to mess you up. So make sure that exactly the way you write it, that's the way you type it in. All right, let's look at the next one. We're going to look at log 657 minus log 203. What should the value of this expression be if we just simplified it into a single number, rounded to 4 decimal places? Anybody got an answer for it?
2.8160.
For this one here?
Yeah, I think so. That's what my calculator gave me. Oh no, okay. Maybe I put an extra parenthesis. Hold on.
Anybody get something different?
Yes, I got 0.51101.
Yeah, I think that's what I got too. I'm just double checking now. Yeah, I'm getting 0.510, and then we can round this one up to a 1. Yeah. 5101. Anybody have any question about those problems? They seem painfully simple, right? And that the truth is because they are. So don't get in your head and then try to make it more complicated than it needs to be. You need to be able to read the instructions and then based on the instructions, sort of discern how complicated the problem actually is. Because if you go into a complicated problem thinking it's simple, you'll probably get the wrong answer. Then if you go into a simple problem thinking it's complicated, you're probably going to mess yourself up there too. So you need to be able to assess basically the complexity of the problem. Let's look at some word problems. Well, maybe they're not word problems per se. They sort of are, but we're going to solve the problem And this is a chemistry problem. But as I said in previous lectures, chemists use logarithms all the time. In fact, when you're measuring the acidity or the basic or alkalinity of water, you use a measurement called pH to describe how acidic or how basic the water is. So we're going to look at a problem here, and we need to round our answer to the nearest tenth. Does anybody know what decimal place the nearest tenth is?
The second one?
It's the
First one?
first one after the decimal. Use the formula. So we're going to use the formula for pH, which is pH is equal to negative log of H3O plus. Okay, so in these kinds of problems, they will give you this formula which has a logarithm in it. See, we have the common log of H3O plus. You don't want to confuse yourself. H3O plus is simply a chemical called hydronium. Sometimes in chemistry, hydronium is written as H3O plus. Sometimes it's written as just H plus. But basically, what makes a liquid or a solution more acidic is how many hydrogen protons or hydrogen atoms are dissolved in that substance. Okay, so all we need to know is if they give us, let's see, we're on number 5. They'll give us some component of this equation and we'll have to solve for some missing variable. So find the pH if our hydronium concentration is equal to 5.8 times 10 to the negative 10 power. So I want you to think about that for a moment and try to see what do we have to do to solve this problem, to find the pH. And let's open it up as a discussion. How do you think we go about finding the pH if we've been given this formula and this value for hydronium?
Are you going to plug the 5.8 times 10 negative 10 into where the H3O plus is?
Absolutely. That's all we're going to do. So you can think about this formula as just a simple plug and chug type problem where we're going to say pH is equal to, the formula says negative log, and then here inside the log, we're just going to type in our 5.8 times 10 to the negative 10 power. And again, remember, brackets and parentheses are the exact same thing. So since we have all of this, and we can plug this into the calculator, it should just directly spit out what our pH is supposed to be. So we just simply type into the calculator, negative log 5.8 times 10 to the negative 10 power, close up our parentheses, and then you let go and let God, you just hit that enter button, and we get a pH of 9 point, and then it said round to the nearest tenth, which is the first decimal place, so we can leave it at 9.2. Okay. This number is actually really small. If I were to write this not in scientific notation, that's what this is called, where you have times 10 raised to a power, then what this decimal number actually looks like is 0 point, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then 5, 8. These are the same value. But it's really a lot easier to write it in this condensed scientific notation form than it is to write out all of these zeros. And then furthermore, rather than talking about the acidity of a substance or a liquid by using this ridiculously long decimal number that has all of these trailing zeros in the front of the value, why don't we throw that into a formula that spits out a nice number? And so that's how the pH scale is determined, right? The pH scale goes from 1 to 14, where 7 is neutral. So this would be like the acidity of water. 1 below 7 would be a very acidic liquid or solution. And then if you're at the 14 range, you would be very basic or alkaline. So if you're between 7 and 14, you would be very basic. So it turns out that, we got a pH of 9.2. So if I asked you whether this was an acid or a base, you should be able to determine that this is a base because it's between 7 and 14. But this isn't a chemistry class. I'm just going to ask you to get that number. There it is, 9.2. Okay, let's look at another one that uses this formula. Let's find H3O plus, our hydronium concentration, if we're given a pH of 10. Remember, the formula that we need is pH is equal to negative log of your hydronium concentration. So can anybody tell me, how would you set up your formula so that we can begin solving it? You don't have to give me the answer, but just how would you go about setting this up?
Put your 10 in front of the equal sign.
Absolutely. Okay. So because we were given pH, we're going to say 10 is equal to negative log of our hydronium concentration. And if it's simpler to just call this X, so you don't have to keep writing H3O plus over and over again, that's fine. We're just solving for our missing variable. Okay, so this, I think, is a little bit complicated, at least in logarithmic form. Remember that this log has an understood base 10, so I'm going to write that in. And it's base 10 because it's a common log. But the first thing that we need to do, it might be super helpful to convert this to exponential form so that we can solve for x. But first, we sort of need to move this negative sign over to the other side. So one thing that you might do is just divide both sides by -1. And we can do that even though this is still a log, because we have -1 times this logarithmic expression. So if we're multiplying this -1, this negative sign, then we can divide it away by dividing it on both sides. So those rules still apply even though we're working with logs. So that will cancel out the negatives here. And we'll get 10 divided by -1 is -10 is equal to log base 10 of x. And then what I would say is at that point, you can convert to exponential form. Can anybody tell me how you would write this expression in exponential form? Let me go ahead and label these things, right? This is the base, which means this guy is the exponent. and this guy is the argument. So how would we go about writing that in exponential form?
Ten
Okay,
to the negative 10th power
cool.
equals X.
Yeah. Well, that's nice because now X is isolated. So we could find 10 to the negative 10th power. We could throw that in the calculator and see what it tells us. Most calculators will probably already be set up in scientific notation, their outputs. And that's what this is saying. It's saying that our answer should be 1 times 10. That's what the E means. So let me write down this output. When you throw this into the calculator, most calculators will spit out 1e negative 10. And what you need to translate that to is that the E is saying times 10 with an exponent of negative 10. So 1 times 10 to the negative 10. So this is our hydronium concentration, what we were looking for, H3O plus. Does anybody have any questions about that? Questions, comments, or concerns?
Is this going to be in homework or on the test?
Both.
Both, okay.
Okay. Okay, I got another set of word problems for you guys. Well, one more word problem. I'll write it down first. The population growth of some species of animal is described by the function f of t is equal to 400 times the log of 2t plus 3, where t is measured in months. That is in months. Here's the moneymaker. Here's the question. Find the population after 6 months. If only I could spell today. Post introduction to some area. Okay, so find the population after they've been this species has been introduced to an area after 6 months. So having read the problem and maybe needing to read the problem once more, can anybody tell me how we would go about solving this problem? What has been given to us and what do we need to find?
Just replace the t with the 6 months.
Yeah, we're legitimately just going to take this 6 and throw it into the formula. So all we need to do is type into our calculator 400, and you can put times there if you want, but the calculator will understand if you don't put the multiplication symbol that this is 400 times log of 2. Now here you do want to put either a multiplication or times 6. So I usually put another set of parentheses like so, plus 3, right? But that's just my personal preference to use parentheses to indicate multiplication. You can put the little star, the asterisk button, whatever you need there. And then we're just going to get the calculator to give us the output. So again, because we're typing in a lot of stuff, just be careful when you're typing it in. 400 times the log of 2 times 6 plus 3. Close the parentheses. That looks like what I wrote down. I hit enter. And my population should be about 470.43 65036. Okay. This question did not ask me or did not tell me specifically what to round this value to. But let's try to use some common sense here. What does this number represent? Like, what are we measuring here? Based on the prompt that was given.
Population.
The population of some animal species. Now, we could have 470 animals. We could go out and count them. But let's say excluding situations where you are mutilating and cutting these poor animals, these poor creatures into fractions of an entire creature. Can we have 0.43 of an animal?
No.
No.
No, so we're just going to go ahead and say we have 470 whole animals. We'll just round down. Now, if that was, we're just rounding to the whole number. Because we count animals in whole numbers. Okay, does that make sense? Does anybody have any questions or comments about that problem? Okay. Let's look at number 8. This is another find the value problem. And we're going to approximate to 4 decimal places. ln 815 times 34. And I should take a moment here to clarify that on the calculator, online, a lot of times you will see something that says ln of x. This looks like in, but it is not in, it is ln, which in your calculator you might see a function that says ln like this. And ln stands for natural log, which is another very commonly used logarithm in science and engineering applications. This log is log base e, if you recall that special number that we talked about on Monday. E is about 2.71, blah, blah, blah. Nobody really, except for engineering and math nerds, memorizes what that value is. But if I went to the calculator, I can bring up 2.718, blah, blah, blah. So that's the base here. This is what the natural log is essentially doing. We just don't write it like this. We write it as ln. So it's a different button in the calculator. So when we evaluate something that has an ln, we're going to use the ln button, which typically your calculator has both a common log and a natural log button. Okay. But this is just like evaluating those common log problems that we looked at the beginning of class. We're literally going to just type ln 815 times 34 in the case of this problem. Close up our parentheses and then hit enter. Okay. So this should be approximately equal to 10.2295484. And then if we round it off to 4 decimal places, we should have 10.1234. So we'll go look there, and that is not big enough to round that up. So we'll just cut everything off and call this 10.2295. And again, it feels a lot like we're just throwing numbers into this black box, this machine that takes these numbers, does something that we're not even sure it's doing with those numbers, but then outputs some value that we're supposed to just blindly trust. And yeah, it sort of feels that way. What this ln is really saying is that, let's go ahead and write the expression if we wanted to understand it a little bit better, right? If we have the natural log of, we can go ahead and multiply this out, right? The input is 815 times 34, which is really 27710. Okay, 27,710. And that comes out approximately to be equal to 10.2295. If we were to convert this into exponential form, what we would be saying is that we have the base of e, which is the base for the natural logarithm, raised to the 10.2295 power. And that should approximately be equal to 27,710. And we could verify that by just going into our calculator, typing e times 10.2295, and then seeing if we get close to that 27,710. You see that we're off by about 2, maybe 1 and some change, but we're pretty close. If we have a better approximation for this, like if I included all of the decimal places that we got, we should get even closer. So e raised to the 10.22954864, which was that whole output that we got, it's a lot closer to 27,710. But whenever you round, whenever you cut off a number, you've made some sort of error, right? And usually when you make an approximation, you're saying, I'm okay with having some acceptable tolerance of error. Because in engineering and statistics, we don't often care about exact solutions to problems. We just want to be within some tolerance of error. So this is acceptable, okay? Let's do one more. ln of 93 over 23. Okay, so what should we be getting when we output that value? Does anybody have an answer for this one?
1.397105.
Yeah, my calculator.
Oh, and then more. 2772.
Yeah, but we just need 4 decimal places, right? So we'll just cut it off at this 71, and then the 0 will not round up the 1, so we can leave it here. Okay. So does anybody have any questions about those? I know we went very quickly through that section. Okay. Now I know that this is this is uncharacteristic for our class, at least the rate at which we're going, but we're going to take a 10-minute break now and then get into solving some equations. Okay. So let's come back at let's call it 1:15, 1:16. Okay. Continue recording. So we're trying to find this missing value x, which is like we're trying to say 4 raised to some power gives us this number. So we could try to guess around to see, 4 raised to what power gives us this. And that might be a good strategy, right? In the past, I described this as matching the bases. So what we might try to do is take the base of 4 and we could try to write that as 2 to the second power, right? Something raised to some power. And we could try to do that same thing with a 1024 and write it as 2 raised to some different power, but the idea is what we're trying to match the base of 2. So we could try to guess around now and brute force it and try to see 2 raised to what power gives us this big number. So you might guess that 2 raised to the 4th power, but we're still too small there. We can try 2 raised to the 6th power, and we're larger, but we still need to get to 1024, so we can keep going up. Maybe 2 to the 8th power, still too small. 2 to the 9th power, 2 to the 10th power. And there we go. So that's 2 to the 10. Okay. So now that we've written them in terms of the same base, we can rewrite our expression. And my apologies for the train. We can rewrite this expression where we're going to convert this 4 to 2 to the second power. So 2 to the second power. And then we're raising that to the x minus 1 power. And that's equal to, well, we say that we can write 1024. I don't know why this is giving me so much difficulty today. 2 to the 10th power. We can utilize our exponent rule, which says if we have an exponent raised to another exponent, we'll multiply those exponents so that we have 2 now raised to the 2x minus 2, and that's equal to 2 raised to the 10 power. And then since our bases match, we can just say the exponents have to be equal to each other. So really we have 2x minus 2 is equal to 10. And now we can just solve for 10. So we could add 2 over to the other side. Then we have 2x is equal to 12. And then finally divide by 2 on both sides, so that our final answer should be x is equal to 6. And we can check that out, right? So like if x is 6, then this is going to be 6 minus 1, which is 5. So 4 to the 5th power needs to produce this number. So we could check that out in the calculator, 4 to the 5th power. And sure enough, 1024 is what we get. Okay. So that was one strategy that we talked about in a previous class for solving this kind of exponential equation. But that's not the only way to go about solving it. In a lot of contexts, this sort of process can be made much easier by using a logarithm to simplify our expression. If you notice that this equation, as we started off, is in exponential form. We have a base, we have an exponent, and we have some argument or some output. So let's run through this problem again. Same problem, just going to solve it in a different way. So that was 4 raised to the x minus 1 is equal to 1024. So if you were, fresh out of last class, Monday's class, and you remember we were going from exponential form, which looked like this, b raised to some exponent is equal to some output. Then we can convert that to logarithmic form by writing this as log base b now this becomes our argument, and we throw the exponent to the other side. And we'll see if making this conversion from exponential form to logarithmic form will sort of make solving this equation easier. So if I wanted to make that conversion here, I have to identify my base, my exponent, my argument. And so I'm trying to stay consistent with this color scheme. Okay. And I'm going to write down log base 4 of 1024 is equal to x minus 1. And on the face of it, that might not seem simpler, but we could evaluate this part in the calculator, this log base 4 of 1024. And so if we did that, we would have to identify, in some of y'all's calculator, you might have this button that has log, and then a little blank here, and then another blank here. It might be in parentheses like that. If you have a TI or an app that's similar to my TI-84, you might have to look for the log base function. But in any case, we can evaluate this part of the equation. If you have a TI-84 or something similar, if you go to math and you go all the way down until you see log base, we're going to click enter on log base, type a 4 for our base, and then 1024 goes into the parentheses. If we output that value, we should get 5. So now we have the equation that this expression is just 5 is equal to x minus 1. And so if you can use this strategy, this equation is so much simpler than trying to play that game where you match the bases. Because now all we have to do is add 1 to both sides so that we isolate the x. X is equal to 6. We get the exact same answer, but by using the log function, log base 4 function in the calculator, there are fewer steps here. And you don't have to play this guess and check method where you're trying to match the bases. Okay. So we're going to try to use this strategy on another problem, just so that we get used to it. But before that, do we have any questions here? Are you guys just ready to jump into the next one? Okay. Let's look at another one. we have 5 raised to the 3 minus x power is equal to 20. And we're going to solve this equation, and then we're going to round to the nearest thousandth. So the nearest thousandth is 3 decimal places, okay? Here, if you were sort of on autopilot and you're very comfortable with that matching the bases method, you would see that we could not match the bases here. 5 is a prime number, so we could only write that as 5 to the 1 power. And then 20 cannot be written as 5 to some power. So right away, we're stuck. We can't use that matching the bases method. So what we want to do is convert from exponential form to logarithmic form. So I want to identify the base, the exponent, and then the argument. I want to rewrite this equation as log base 5 of 20, and that should equal 3 minus x. Are you guys okay with that step? The second step is going to be just to simplify the log expression in the calculator. So this left-hand side of our equation. Okay, so in this particular equation, it's on the left-hand side. But we just need to throw log base 5 of 20 into the calculator and then see what it spits out. You'll see that because we can't match the bases between 5 and 20, whenever the bases can't match, you're going to get a really ugly decimal number. And these instructions will tell you to round to some decimal place because these are really ugly numbers. So let's take a look and see what we get. So going to go to log base 5. I'm going to throw 20 as my argument. And then the output is 1.8613, blah, blah, blah. Okay. So I'm going to keep all of those decimal places until the very end. I know it's very tedious and annoying, but we're just going to do it. 1.8613, 53116. And that's equal to 3 minus x. Now, I think that a lot of students tend to get some sort of anxiety or trepidation whenever they have a weird decimal number and then whole numbers over here. There's like some subtle subconscious belief that whole numbers and decimal numbers can't interact with each other, especially crazy decimal numbers like this. But they're all just numbers, and we're going to treat them the exact same way. I'm just going to isolate my negative x here by subtracting 3 on both sides. So now we have negative x is equal to whatever this is, 1 point blah, 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 minus 3. And hopefully we've kept that output in our calculator so we don't have to type it in again. I'm just going to hit subtract 3, and that's going to be my previous answer, minus 3. And we should get negative 1 point blah, blah, blah. Okay, so let's keep all those decimal places. Negative 1.1386468884. You'll want to double check to make sure that you've written that correctly, because I wouldn't want you to make a careless mistake. And then we need to get x by itself. Currently, it's negative x. So how do we get rid of the negative sign?
divided by negative 1.
Yeah, we'll divide by -1 on both sides. So there we go. X is equal to, now a negative divided by a negative is going to be positive, so we're just going to have positive 1.138646884, and rounding to the nearest thousandth. So if we're rounding, we're going to get an approximate answer. Nearest thousandth is the third decimal place. So here, and that 6 is large enough to bump this up to a 9. So our answer should be 1.139. But I definitely feel like the hard part of this problem is just converting this from exponential form to logarithmic form, evaluating that logarithm in the calculator, because this is just a linear equation after that. We're just going to add or subtract or multiply, divide, you know, however we solved linear equations before, we're going to do that same thing to isolate the x. Okay. So don't overcomplicate it once we've gotten past this sort of new bit that we've done at the top. The downhill stuff is old news in some sense. Okay, I'm going to give you a problem and have you guys take about 3 to 5 minutes to work it on your own. So I want you to solve this, and again, round to the nearest thousandth place, so 3 decimal places. 8e raised to the 9x plus 6 is equal to 6. Does anybody have any questions? Or is anybody stuck?
Do we have to multiply like 8 times e to get the base? To have the
So
base or no?
that's a really good question. The answer is no, you don't. But you're right that currently you have 8 times e raised to this weird power. So like our order of operations say we would have to do the exponent before we do the multiplication, right? Like if we knew what x was. So instead of trying to multiply the 8 times the e, your first step would be to divide the 8 over to the other side. Let's just move it away from our exponential expression.
Okay, thank you.
Yeah. So can anybody tell me what they did after this point?
Convert to logarithm form.
Yes. Yeah. So we're going to convert to, we'll just call it log form. And how did you write that down?
Log e parenthesis 0.75.
That works. I'm going to leave it as 3/4 though, because I like fractions.
Oh, 3/4. Okay. Well,
But 0.75 is the same value, so you're perfectly fine to leave it as 0.75.
well, 9x plus 6.
Okay. Yeah. And then if you recall from a little bit earlier today, I said that if we have log base e, this is the same thing as the ln button in your calculator. So you could do ln of 34 is equal to 9x plus 6. Or you could put log base e of 3/4 into your calculator using that log base button. Either way, you'll get the same value. So just to show you guys natural logarithm of 3/4, you get this negative number, negative 0.287, blah, blah, blah. Or if you had done log base, and you would put e for that base and 3/4 as your argument, you get the same thing. Again, natural log and log base e are the same. Okay. So we'll just replace this part of the equation with this really, really not very pretty decimal. Negative 0.28768 207.25. 207.25 is equal to 9x plus 6. And even though that this is an intimidating decimal, we're just trying to isolate the x now. So we could subtract the 6 over to the other side. Then we just divide by 9, and then that is the value of x. So minus 6, minus 6. Again, with decimal numbers like this, you'll want to just keep that output in your calculator so that you can just subtract the 6. And then we'll just divide that number by 9. So we ended up getting negative 6.287682072 is equal to 9x, then dividing by 9. So you get x is approximately equal to, and then we just wanted 3 decimal places, so negative 0.699. Does anybody have any questions, comments, or concerns about that problem? I did throw you into the slightly deeper end of the pool there by throwing you into the problem, knowing that this 8 would give you an issue. But I sort of want you to basically exercise those critical thinking skills. Like when you run into something that looks strange, what are we supposed to do there? Okay. So now I'm going to give you another problem and give you another 3 to 5 minutes to work it, maybe a little bit more. Let's look at this one. We're going to solve and round our answer, final answer to 3 decimal places. So 3 times 10 raised to the 4x minus 5 power plus 9 is equal to 72. Okay. And maybe we can talk this one out loud. What do you guys what are you thinking is going to be the first step to a problem like this? What feels like the first move?
Move the 9 to the move the 9 to the other side.
Yeah, that's perfect. So what we want to do is isolate the exponential expression. When you look at something that's complicated like this, I want you to zero in on what it is that we need to isolate. And we need to isolate this exponential thing so that we can then switch it to logarithmic form. But until that guy is isolated, we won't be able to switch to logarithmic form. So the easiest operation we can do to start isolating that term is just to subtract the 9 over to the other side. So we'll be left with 3 times 10 raised to the 4x minus 5. And that's equal to, well, whatever 72 minus 9 is, 63. Yeah. Okay, so again, we're still trying to isolate the exponential expression. So how can we move the 3 over to the other side? What operation will we do to move that 3 over?
A division.
We'll do division, right? So since this is 3 times our exponential expression, we're going to divide 3 on both sides. So we end up getting 10 raised to the, at this point, because we don't have anything sort of attached to our exponential expression, we don't need the parentheses, although you could leave them if you wanted to. But this is going to be equal to 21. So now what is the next step?
Convert to log form.
Yeah. So what would I write down to convert that to log form? I'll write log for sure.
10
Log base 10.
times 20, in parentheses 21
Parentheses 21, yeah.
equals 4x minus 5.
Yeah. And so now we can evaluate this in the calculator, get that number, and then all we have to do is go about isolating our x. So remember that log base 10 is the common log. So we can just use our log button in the calculator. And we don't have to put a 10 because the calculator understands that's 10. Log of 21 is this ridiculous number. We'll just bear with it. 1.3221929.5 is equal to 4x minus 5. Now what is the next step that I have to do?
Add 5 to both sides.
Yeah. Add 5 to both sides. So this will be 6.32221929.5 is equal to 4x. And then what is the final step?
Divide by 4.
Yeah, divide by 4. So x is going to be approximately equal to 6.322219295 divided by 4. And I get about 1 point, and we need 3 decimal places, so 581. Anybody have any questions there? Okay, so notice that in these problems, because the instructions specifically say round to the nearest blank value, they're allowing you to use a decimal number or decimal approximation for your final answer. There are certain problems that will say express all of the solutions in exact form. Do not round. Okay, so for these kinds of equations, we're going to have to take care to not plug something like this into the calculator, but leave this as log of 21 as we continue to sort of move and do operations to the problem. So what I want to do is just show you briefly, this is an approximate answer. What would the solution look like if we found the exact solution and did not round? Okay, so I'm going to write down this problem one more time, and we'll run through it. Find the exact solution. Three times 10 raised to the 4x minus 5 is being added to 9. That's equal to 72. All of the steps of this problem are going to be virtually the same, but at the end, we're going to do a little less work, and we're not going to use the calculator. So the steps begin just like the other problem. We wanted to isolate the exponential part of this equation, and we did that by subtracting the 9 away from both sides so that we got 63 is equal to 3 times 10 raised to the 4x minus 5. We then divided both sides by 3. And we got 21 here is equal to 10 raised to the 4x minus 5. Then we said, okay, we'll convert that to logarithmic form. Exact same process. We're going to write log base 10 or just log. I'll leave log base 10 of 21 is equal to 4x minus 5. Now imagine that we did not take this. I'm going to sort of put a box around this logarithmic expression. Imagine that we did not put this in the calculator. To isolate the x, we can still do that. We don't worry about what the actual value of log base 10 of 21 is. We're just going to add the 5 over to the other side. So we would get this expression that says log base 10 of 21. And if we added 5 to both sides, I would just write plus 5 on this side. And I would just get 4x by itself. So this is like I have that log expression, but I've moved the 5 over to the other side by adding it. And then I would still need to divide the 4 over to the other side to get the x by itself. So what I would get is x is equal to whatever the result of this addition is. Again, I'm not going to explicitly put this into the calculator. I'm just going to leave it like this. I would have to divide the 4 on both sides of my equation. So I can just write divided by 4 over here since these 4's cancel out. This expression here, log base 10 of 21 plus 5 over 4, that is the exact solution. That is exact form. When you leave this expression in logarithmic form, we haven't made any rounding error. That is the exact answer. In the same way that when we were looking at quadratic equations and we left some things in radical form, right? Rather than saying that, for instance, the square root of 2 is approximately equal to 1.4. Well, if we cut it off there, then we don't have an exact number because root 2 is not equal to 1.4. It's equal to 1.4 and then continuing with these weird irrational decimal values. Similarly, when we cut off our value here and we said our solution was 1.581, if I were to put this expression into the calculator, so don't mind me, I'm going to set this up as a fraction. Log base 10 of 21 plus 5 all over 4. Okay, that's exactly what we wrote down. Exactly what we wrote down there. We should be getting something close to this, right? If this is approximate, this should be close to our answer. And it is. But leaving it in this logarithmic form is the exact answer. We haven't made any rounding or estimations or cutting off of any values. So when they ask for your solution in exact form, we won't be throwing that logarithm into the calculator to evaluate it. We're just going to leave it as it is, this big symbolic chunk, and we can still add numbers to it, divide it by something, and we'll just leave that expression as something that looks a little bit more complicated, but is formally exact. That being said, let's look at another problem. So we need to solve the equation and express the solutions in exact form. So I'll guide us through this one. We have the natural log of 5x minus 6 plus the natural log of x minus 6. And that's equal to the natural log of 36. Okay. Now I know that Monday was a long time ago, but ignoring this right-hand side of the equation, if we have two logs that are being added to each other, can we simplify this expression by condensing them into a single logarithmic expression?
Yes.
How would we go about doing that using our log properties from last time?
Just combine the 5x minus 2 plus x minus 6.
And how would we combine them? What would you write down?
6x minus 12.
6x minus 12. Okay, I see what you're doing. It's a good attempt, but wrong. Okay.
Would you distribute
No.
in a way?
You'll have to remember this log property from last time. So the log property here said that if we had a log of x plus a log of y, and those are the same log base, that we can combine them into a single log, but we're going to multiply their arguments. Does that ring a bell? So since we have two logs over here that are being added to each other, and they're natural logs, then we can write this as the natural log, and then we're going to multiply their arguments. Okay, so this 5x minus 6 and this x minus 6 are going to play the role of our x and our y here in the formula. And we need to multiply them out. So I'll have 5x minus 6 times x minus 6. Okay, and I'm sort of ignoring this for a second, just because we sort of need to deal with this. How do I multiply these two expressions out? Or maybe, Brooks, is that what you were getting at?
Yeah, so it'd be 5x squared.
Yeah, so we would have ln of 5x squared Yeah, let me go ahead and write this down. We're going to throw these arrows because when we multiply polynomials, we distribute them out. So 5x squared minus 5x times negative 6 would be 30x, then another negative 6x, then a positive 36. We can go ahead and combine like terms. So we have ln is ln of 5x squared minus 36x plus 36. And that's equal to, we didn't touch this side over here, ln, and I'll be consistent and use brackets now, 36. Okay. Does anybody have any questions up to this point? We're definitely not done, but I just want to see, does anybody have any questions? Well, this is actually really nice because if we have the log of something is equal to the same log of something else, then those inputs that we're throwing into the log function, they have to be equal to each other. Otherwise, the entire expression won't be equal to each other, the entire equation. So this is sort of like where our bases matched when we were looking at exponential equations. If the log bases match here on both sides of the equation, then the inputs for those logs have to be equal to each other. So we can just say, ignore the log bases. And now we have 5x squared minus 36x plus 36 is equal to 36. And that is just a quadratic equation. So I'm going to write right here, bases match. So ignore the log base. So there's multiple ways to solve this quadratic equation. The first step when you're solving quadratic is to get it into standard form. That is, we want the equation equal to 0. So I'll subtract 36 on both sides. And it turns out that this cancels out to 0. This also cancels out to 0. 5x squared minus 36x. And then this thing is factorable. So we're going to use the zero factor property, factor this, and then solve our two equations if we get two equations. Okay. So it looks like the common factor here is going to be x. So I'm just going to factor out an x. And that will leave us with 5x minus 36 is equal to 0. And I've run out of room here. So let me just go to the top of the next page. The zero factor property says that I can set x equal to 0 and 5x minus 36 equal to 0, where now this equation is already solved. And I can solve this linear equation by moving the 36 over to the other side and dividing by 5. So x is equal to 36 over 5. But we're going to want to be very careful here. For these logarithmic equations, we want to check our solutions. So yet another kind of equation where we're going to want to check our solutions. And I will just put it plainly that you need to plug these solutions into the original problem. And if you get an error in your calculator from plugging in that solution, then that solution is not valid. So for instance, if we plugged 0 in for x here and tried to evaluate the natural log of 5 times 0 minus 6. Natural log of 5 times 0 minus 6. Non-real answer. So I have an error when I plug 0 into the first expression. That error tells me already that 0 is not a valid solution. But if you wanted to, you could check in the other expression too, right? So ln of 0 minus 6, another error. So right away, if we plug that solution into both of these, we get errors. So as soon as you get a single error, you have to throw that solution away. For 36 over 5, we could check that as well. As long as we didn't get an error, we should be safe. So 36 over 5 minus 6. No errors there. ln of x minus 6. So that would be 36 over 5 minus 6. No error there. So we're good. That's going to be our single solution. Does anybody have any questions about that problem? Let's look at another one. And they're not all solved the exact same way. They're all solved a little bit differently. So you're going to have to think about, what strategy could I use to solve something that looked like this? Log base 5 of 3 minus 4x, that's equal to 2. Okay, so I'm going to give you guys about 3 to 5 minutes to think about this problem. Try to work it out if you can, but if you get stuck, just let the juices churn for a little bit, and I'll jump in and ask you in a second if you need a little gentle nudge in the right direction. Okay, so does anybody have any ideas or strategies that they think would be like the best first step for a problem like this? What are some things that we tried to do here?
I have idea, but I don't know if it's correct.
Sure. I mean, this is the creative process of math. Like, you might not know when you look at a problem how to go about solving it, but you sort of jump in with some ideas, and it might not feel correct, but let's see where it leads us, and then determine if it's correct after that. So what was the first thing you did?
To turn to an exponential.
Okay. So we're saying let's try and change this to exponential form. Okay, so how did you write that down?
5 times 2.
5 times 2 or
Me,
5
parenthesis 2. Yeah, it's times 2 now.
raised to the second power?
Maybe I make it wrong. See?
Yeah, maybe. I think that this is the right thing, but
Okay.
remember that this is the base. This is the exponent. And then this guy is the argument. So if we wanted to properly change this to exponential form, which is the first step that I would do, I would write this as 5 raised to the second power, and that's equal to 3 minus 4x. Okay. Did anybody else do that for their first step?
Yes.
Okay, cool. Well, that was definitely the path that you needed to go down. I'm sort of curious about any other strategies that we tried here, but in the interest of time, I'm just going to go ahead and proceed with this path. Vanessa, you said you did this method as well. What was the next step?
I don't know if it's right, but I evaluated the 5 to the second.
Yeah, and you got 25, right?
Yes.
And that's equal to this. Well, then can anybody tell me what kind of an equation this is?
Linear equation.
Yeah, so we're just going to solve it the way we've been solving linear equations. We're just going to isolate the x. I will just subtract the 3 over to the other side. So now this should be 22 is equal to negative 4x. And then we could divide both sides by negative 4. And so this reduces by 2. So we should get negative 11 over 2 is equal to x. And that should be our solution. So actually this problem, once you unlock the secret to converting this to exponential form, right? It became a fairly simple linear equation. But you have to let those juices churn, right? We have talked about converting from exponential form to logarithmic form and vice versa. So for this kind of an equation, well, we might try that as one of our first strategies. And if that doesn't work out, that's fine. Don't get stuck there. Don't get married to the idea that has to be the only way. Try one of the other strategies that we've talked about. And if that doesn't work, then try some other strategy, right? At some point, when you practice enough of these, you develop a sort of dexterity or familiarity with what strategies might lead you in the right direction. And so even though we do feel like we're wandering in the dark a little bit, which is a completely normal feeling in mathematics, that's the creative part of it. As long as you're not making up your own mathematics or completely ignoring symbols or numbers or negative signs, then you should be good to just tinker around, okay? Let's go ahead and do another one. So we'll do this one together and we'll talk it through. So we have log of 5x is equal to log of 2, let me throw parentheses so that makes more sense, plus log of x plus 2. Okay, so looking at this problem, does anybody have any idea or inclination, right? You might not know the exact, correct thing to do, and that's fine. You just have to get comfortable with being uncertain. But we can have an inclination or a feeling as to which direction we have to go. Okay, so looking at this problem, does this feel similar to something that we've done before? Is there something that's jumping out at you that you want to try to do on this equation?
Is to add the log 2 plus log x plus 2, multiplying this time.
Yeah, so we could use that log property, right? The log property says that if we have log of something plus log of something else, that we can combine those into a single log and then take the x and the y and multiply them, right? So let's work that out. Let's try that. So we'll have a single log, but inside that log, we'll have the 2 times the x plus 2. And we didn't do anything to the left-hand side, so we'll leave that alone. Well, we can just sort of let this ball roll downhill and say, okay, let's go ahead and multiply out this expression. We have log of 2x plus 4. And that's equal to log of, and let me be consistent if I'm using brackets or parentheses, so I'll call this a bracket instead. All right, so we're here now. We have log of 5x is equal to log of 2x plus 4. What do you think we do now? What does it feel like we could do?
Do we have to ignore the log and just resolve the numbers?
Yeah, because this log has the same base as this log. So we have log of something is equal to log of something else. So if these two quantities are equal to each other, then their inputs have to be equal to each other, which means we can sort of ignore the logs. And that means that 5x is equal to 2x plus 4.
Take away the 2x on both sides.
Yeah, exactly. Now we're just trying to isolate the x. So I'll subtract 2x on both sides. This is going to be 3x now is equal to 4. And then we could divide by 3 on both sides. So x is equal to 4/3. Okay, guys, that's all we have today. We made it to the end of our lecture. I know it sort of feels, I feel a sense of joy, a sense of elation that we've made it this far. I'm very proud of all of you guys for sticking with me for this long. It's been a joy. It's been an honor to get to know y'all this semester. And we just have to get through the final now. Okay. So remember that I am still here through next Thursday. if you need to communicate with me, if you need to set up a one-on-one tutoring session, if you want to drop into my Math World hours, I am available. I want to support you as you prepare for the final. And I'll post an announcement in Canvas here in a little bit with those details about the final that we discussed at the beginning of class, okay? But I am still here. We got one last thing we need to take care of, and then we're done. Probably done with math for the rest of our academic career, right? That's exciting. Okay, but we need to get through this final, right? So get the support from me, from other tutors if you need it, reach out, and let's get this done, okay? If you have any questions, as always, you're more than welcome to hang out with me after everybody leaves. Send me a message if you need some help, some support, okay? Good luck with your studies, and I'll see you around. Get vaccinated, and then I'll see you around and face-to-face maybe one day.
Thank you.
Yeah, you're welcome.
Thank you.
Take care, everybody.
Thank you.
Thank you.
Thank you.